Okay, now I don't want you to get the wrong impression. So we checked that x mu dot x mu was Lorentz invariant. But for example, if you took p mu dot p mu, and this would be equal to e squared minus p dot p. That would also be Lorentz invariant. And in fact, more generally, if you were to take any two vectors, so for example, x mu dot p mu, this would be e times by t, so the first component of x times the first component of p, minus, it will be x dotted into p. These two would also both be Lorentz invariant, meaning invariant under rotations and invariant under boosts. Okay, so this dot product between any two 4 vectors is Lorentz invariant, just like the dot product between any two 3 vectors is rotationally invariant. Okay, good. Okay, so I told you this is bad notation, so let's now try to fix the notation and let me tell you what actually the standard notation is. So let me now clean a little bit of space here. There we go, so that can disappear. And let's clean this. Great. Okay. So when we have a vector with an index up, we call this, so this is t, x, y, z, and we call this a contravariant vector. And the way that you should think about this is that this index mu can take the values 0, 1, 2, and 3. And in particular, x0 would be t, x1 would be x, x2 would be y, and x3 would be z. So this index mu takes the values 0, 1, 2, 3, and it just indexes the different components inside this vector. There's also a vector with an index which is down. The vector with the index down is t comma minus x. So that means t minus x minus y minus z, and we call this a covariant vector. Okay, and if I plug in values for the indices here, well, x0 would be t, x1 would be minus x, x2, lower 2 would be minus y, x3, lower 3 would be minus z. And okay, so this is just the notation, contravariant and covariant vector. Now, why do we introduce these two? And here's the key idea. All covariant vectors transform in the same way. So that's why we introduce covariant vectors. And all contravariant vectors transform in the same way. So all of the notation that we've been introducing are so that we can capture how these different objects transform. Why is this so important? Well, it's important because we want to write down equations that are the same in all Lorentz frames. We want to write down equations that don't change if we do a boost or a rotation, because boosts and rotations are symmetries of nature. Now, let me explain to you the correct way to write down our dot product. So this is, we kept saying before we had a bad notation. Now let's write down our Lorentz invariant in a good notation. So the good notation is we write down x mu. So you can call that mu a superscript, or you can say we've written down the contravariant vector. Either of those is okay. And we multiply that with the covariant vector, or something with a subscript. Notice here that the indices match. So what I mean when I write that down, I mean I've got an upper index which is a mu and a lower index which is a mu. If I had, say, x alpha, x beta, those indices don't match because they're not the same. So when I say the indices match, what am I saying? The upper index is a mu and the lower index is a mu. When the indices are repeated, so they're also repeated, then we say this is called a contraction of the indices. And what this means is whenever there's an index, an upper index and a lower index that is repeated, it means that these indices are summed. So we've got x0, x1, x1 plus x2, x2 plus x3, x3. And this contraction of the indices, which implies a sum, so whenever the indices are contracted, a sum is implied. This is called the Einstein summation convention. So whenever you see an index upstairs and an index downstairs, or a superscript and a subscript, or a contravariant index and a covariant index that is repeated, it means that that index is summed, and that's called the Einstein summation convention. Okay, let me just clear some space. Now let's evaluate what this sum is. Well, we know what the contravariant and covariant components of our vectors are. So x0 upstairs is t, x0 downstairs is t. So the first term is just t squared. For the second term, x1 up is x, x1 down is minus x. So we've got minus x squared. For the third term, x2 up is y, x2 down is minus y. So we've got minus y squared. And then x3 up is z, x3 down is minus z. So we've got minus z squared. And this we see is just our Lorentz invariant. This quantity will be the same in all Lorentz frames. So if you contract indices of two vectors, you will get a scalar. Now, let me make one other comment. If you were to take x mu up and x mu up, let's say you took this and you try to apply the summation convention to this. So x naught up times x naught up plus x1 up, x1 up plus x2 up, x2 up. So what would this be? Well, again, we can plug in components and we get t squared plus x squared plus y squared plus z squared. Well, this is not Lorentz invariant. If it's not Lorentz invariant, that means it's not boost invariant. It takes a different value in all different inertial frames. So it's not meaningful for physics. This is not a meaningful quantity at all. We would not be interested in it. So whenever you perform a contraction, you can never contract two indices up or two indices down. That doesn't give you anything meaningful for physics. You must always contract one index up and one index down. So that's a very important rule. You must always contract, and you can say an upper index, a superscript, or a contravariant index, and a lower index or subscript or a covariant index. So the Einstein summation convention is always defined with an upper index and a lower index.